Tenant isolation is fundamental to the design and development of multi-tenancy applications. In a multi-tenant architecture, multiple instances of application operate in a shared environment to achieve cost and operational efficiency. So in this session, we look into various multi-tenancy design patterns on Amazon RDS for PostgreSQL and MySQL, and Amazon Aurora with PostgreSQL and MySQL compatible databases for achieving scalability, cost, and operational efficiency. And most importantly, security. My name is Krishna Sarabu. I'm a Senior Database Specialist Solutions Architect at AWS. We'll start with introduction to Amazon RDS and Amazon Aurora to set a quick context recap. We will dive deep into various multi-tenancy deployment models and Amazon RDS for PostgreSQL and MySQL and Amazon Aurora. We'll also discuss sizing considerations. We'll also look into Amazon Aurora Serverless V2 and how it can automatically scale up and down in place instantly and without disrupting your multi-tenancy workloads. We conclude our session with design best practices and open up floor for Q&A. So before we get into design patterns, just a quick recap to set the context. Amazon Relational Database Service, or RDS, is a collection of managed services that makes it simple to set up, operate, scale databases in the cloud. Amazon RDS automates common administrative tasks, such as performing backups and patching the database software. With optional multi-AZ deployments, Amazon RDS also manages synchronous data replication across availability zones with automatic failover. Amazon RDS supports data encryption at rest and in transit. It provides cost-efficient and resizable capacity while managing time-consuming database administrative tasks, freeing you up to focus on your applications and business. You can choose from several popular engines: Amazon Aurora with MySQL and PostgreSQL compatibility, RDS, MySQL, MariaDB, PostgreSQL, Oracle, and SQL Server. So this means that the code, applications, and tools you already use today with your existing databases should work seamlessly with Amazon RDS. So for RDS, PostgreSQL, and MySQL, you can add up to 5 read replicas for scaling out reads. So the recent feature we introduced to RDS PostgreSQL version 14, which supports up to 3 levels of cascading replication. That means you can add up to a total of 155 read replicas for scaling out your read-intensive workloads. As with all managed services at AWS, you pay only for the resources you use. Amazon Aurora is a MySQL and PostgreSQL compatible relational database built for the cloud. You get the performance and availability of commercial databases with the simplicity and cost effectiveness of open source databases. At core, Amazon Aurora decouples your database compute and the storage. Aurora uses purpose-built distributed storage layer, which stores your data across 3 availability zones. We keep 6 copies of your data across 3 availability zones. And depending on the database size, your data is striped across hundreds or even thousands of storage nodes. So with that, what you get is a better availability, durability, and performance. Amazon Aurora storage is also self-healing. So data blocks and disks are continuously scanned for errors and repaired automatically at the storage layer. And that to be without disrupting your workloads on the database engine. So you can also add up to 15 low latency read replicas to the same storage volume. And you can use these to scale out your read intensive workloads. And most importantly, because there's this separation of compute, we can scale compute separately and independently of the storage layer. So you can scale it up and down, add more read replicas, remove read replicas without having to worry about what's happening to the storage layer. So Let's start with SaaS architecture at very high level, followed by multi-tenancy design models in RDS and Aurora for MySQL and PostgreSQL. So whether you have several hundreds or thousands of applications backed by large number of databases in the enterprise, or independent software vendor making the shift towards SaaS and adopt a shared infrastructure model to achieve cost and operational efficiency. So at high level architecture, there are actually two very important pieces when designing multi-tenancy applications. One important piece is the control pane, where you automate onboarding new tenants, authentication and authorization, tracking metrics, and analytics for tenants, and of course, the billing and so you're basically looking at questions like if you have fully automated provisioning experience along with authentication, authorization, and isolation for each one of your tenants. And also you're looking at questions like, whether you have a rich operational view to find what's happening inside each tenant environment. And then the second piece is the application pane. So this is where you actually have built multi-tenancy services, the isolation at application or service level, isolation at database level, etc. And after tenant is onboarded, how the authentication and authorization works, ensuring that the isolation is built into your application and database stack. So you would typically use services like Amazon Cognito or any external authentication mechanisms, and that would authenticate the tenant and return tenant context. So this is the set of information that represents the tenant they are working on behalf of, which in turn you use that information to isolate the tenant from application to the database layer stack. So all of the SaaS applications that we talk about at AWS, they share common core values. So in the next few slides, I'll focus on various tenancy isolation models and design recommendations. Isolating tenants in multi-tenancy architecture is critical, especially securing the tenant and ensuring that tenants are prevented from accessing another tenant's data. So there are a wide range of factors that can influence how the tenant isolation is realized in any SaaS environment. The domain, compliance, deployment model, and the selection of AWS services, they all bring their own unique set of considerations to the tenant isolation policy. Whether tenant requires a strict isolation, usually, which in turn requires isolating the tenant at infrastructure layer, or you want to pool and share infrastructure resources and with logical tenant isolation for better cost and operational efficiency. No matter what design pattern you use, the key security objective is to isolate and protect the tenant data. So, tenant isolation, resource sharing, security, and performance are key to designing multi-tenancy database architectures. So let's look into tenant isolation design patterns. Let's start with silo model. The tenant data is fully isolated from each other in silo model. So each tenant would have a distinctive representation, monitoring, management, and security footprint. So while SaaS providers are often focused on the value of sharing resources, there are still scenarios where a SaaS provider may choose to have some or all of their tenants deployed in a model where each tenant is running in a fully siloed stack of resources. However, what generally drives adoption of a silo model is strict security and regulatory constraints. For example, tenant-specific KMS key for encrypting data at rest. So that requires SaaS tenants with full stack isolation. Similarly, if SaaS provider wants to offer tier-based approach. The premium tenants with additional subscription fee to have a full isolation stack. You basically create a full stack isolation from infrastructure and application to the database layer. So at database layer, what it means is, you create a RDS or Aurora database cluster per tenant in silo model. So let's now look into the next one, the bridge model. So in bridge model, you isolate the tenants by either creating a database per tenant within the database cluster or by creating a schema per tenant within a database cluster. So the bridge model often represents an appealing compromise for SaaS systems. It enables to share database resources while providing tenancy isolation. More importantly, achieving cost optimization and operational efficiency. On RDS and Aurora, you achieve this tenancy isolation by creating schema per tenant or database per tenant. So one important thing I wanted to highlight here. So in MySQL, the create schema is synonymous to create database. So now let's look into the pool model. The pool model represents the all-in where tenants share all of the database compute and storage constructs. So the tenant data is placed into a common database, common schema, and into common tables. So you basically partition the data at table level to scope and control tenant data access. So this model tends to simplify a SaaS solutions provisioning, management, and update experience. And there are cases where you also adopt hybrid model, right? So often SaaS developers prefer hybrid models and use both silo and bridge or pool models in combination. I mean, this decision could be based on customer tiering, like the platinum customers with additional premium fee, for example, into silo model, or by customers with the compliance requirements. As I mentioned before, you have strict compliance requirements to carry their own KMS key. So then naturally you would put them into a silo model. So now let's look into the model pros and cons. Selecting the multi-tenancy strategy for RDS and Amazon Aurora is influenced by many different factors. Silo is appealing for SaaS solutions that have strict regulatory and security constraints. As I mentioned, basically the tenant-specific key management, for example, right? And also, you want to isolate, your premium customers from noisy neighbors. It also adds advantage of scaling out your tenants horizontally. So with respect to availability, the blast radius can be reduced to per tenant using silo model. And with silo models, cost could be high compared to bridge or pool models. So the provisioning and management is a little bit more complex in silo. For example, onboarding new tenant required automation that provisions new database cluster. And also often you would run into service limitations. Any changes to schema structures need to be coordinated across sprawl of database instances in silo. So it's certainly achievable, but it adds a layer of complexity. Also, the ability to view cross-tenant activity is limited in silo. The silo model makes you work harder to find and introduce tooling to create an aggregated database system view of health that span across all tenants. On the other hand, bridge or pool models have better agility, cost optimization, and operational efficiency. You share resources for multiple tenants using single Amazon RDS or Amazon Aurora cluster and isolate the tenant data by a schema per tenant or a database per tenant using bridge model, or the table data partition using in pool model, right? So with bridge and pool models, the tenants can be affected by noise in neighbor. So you should have an automated tooling to monitor and identify noisy neighbors, and of course, a mechanism to isolate them to reduce the impact for providing better tenant experience. So let's now look into decision metrics and the factors that can influence what isolation model you should pick. So in addition, you also need to look into various other factors for choosing appropriate isolation model for your multi-tenancy workloads. For provisioning and management, the new tenant agility could be faster in pool, moderate in bridge, and slower in silo. If you're planning to use database connection pooling and multiplexing, the silo model requires significant effort. Naturally, right? You need to deploy one single connection pool per tenant, and also the the connection sharing and multiplexing is very poor in silo model. In addition, you also need to look into various other factors for choosing appropriate isolation model for your multi-tenancy workload. For provisioning and management, new tenant agility could be faster in pool, moderate in bridge, and slower in silo. And if you're planning to use database connection pooling and multiplexing, the silo model requires significant effort and least efficient as no database connections are shared between the tenants. But tenants can use maximum DB connection supported by your instance class. And database maintenance operations such as vacuum in PostgreSQL could be simpler in silo, moderate in bridge, and when it comes to the pool model, the tables might be large for pool model based on number of tenants, possibly require additional vacuum related tuning efforts. And with respect to change deployment impact, the blast radius could be significant in pool model versus minimal in silo and bridge. And cross-tenant resource impact, it's not an issue with silo models as the entire tenant stack is isolated, whereas it's moderate impact in bridge model and significant impact in pool model. And tenant level tuning. For example, you'd like to add additional indexes for a particular tenant. That's not possible in pool model. You could leverage partial indexes, of course, in PostgreSQL to an extent in pool model. Rebalancing effort. It's not at all a concern in silo model, but it's a significant effort in pool model. And it's a moderate effort in bridge model. You can, of course, use logical replication in bridge model to minimize the downtime for rebalancing or relocating efforts in bridge model. And with respect to high availability and disaster recovery, database downtime for major version upgrades. It's a standard downtime for silo and of course for pool models, and a little longer downtime for bridge model, depending on the catalog size and the number of tenants. And tenant level availability, silo has highest level of availability, right? And one tenant unavailability will not impact another tenant in silo. And when it comes to bridge and pool models, it impacts all the tenants hosted in the database cluster. Please note that RDS and Aurora automatically fail over your database when configured with multi-AZ. Tenant level backup, it's a least effort in silo and moderate efforts in bridge. You could use PG dump, MySQL dump, PG dump in Postgres, MySQL dump in MySQL for tenant level backups for bridge. And it will be a little complex when it comes to pool because you're using one single table and one single schema for all the tenants. And of course, when it comes to Postgres, you can use commands like copy for copying subset of data, but when you're dealing with a large number of tables, it becomes a little complex. Tenant level point-in-time recovery. Silo is a minimal effort. You can simply perform point-in-time recovery using automated backups, snapshots, or backtracking in Aurora. Moderate effort in bridge model. So you basically need to restore the backup and then export the tenant-specific data. It's a little complex when it comes to pool model. And application dependencies. So with respect to that, the uniform schema name, for example, it's possible in silo and of course in bridge model with databases per tenant, with the database per tenant. And you need to use a different schema name for bridge model with the schema per tenant. And of course, pool model uses the same schema table for all tenants, so that's not going to be applicable there. And per tenant customization definitely is possible in silo as it's completely isolated stack. And bridge model, and of course in bridge model as well, even with the database and schema models. And when it comes to pool model, it's going to be a little complicated. And tenant specific read scaling with additional reader nodes. For example, you wanted to, based on additional subscription option, you would like to give additional reader nodes. And this typically requires least effort in silo. As the entire stack is isolated, you simply create a read replica. But requires moderate effort in bridge model because you have multiple tenants sharing the same database cluster. So naturally, you could use, naturally you wouldn't want to create a read replica. It's going to create a replica for all tenants. But you can possibly use logical replication to set up a replica for reads. With the logical replication, you're going to replicate only the tenant data to the target, and you can allow the tenant to perform the reads from the logical replica. So when it comes to pool model, it's going to be complicated. With respect to security, data isolation is best in silo and better in bridge and worse in pool model as it uses same table for all the tenants. You can leverage features such as row-level security in PostgreSQL to ensure that the tenant will not be able to see the access in another tenant data. I have an example coming in next slide, which I can show you how to use row-level security for isolating tenant data in pool model. And tenant-specific storage encryption key, it's possible in silo, not possible in bridge and pool models. And IAM authentication per tenant, it's possible in silo and bridge models, not possible in pool model. With respect to cost efficiency, infrastructure cost could be very high in silo because you have a fully isolated stack from infrastructure to the database. So naturally, that would push cost a little higher. Versus, it will be moderate in bridge and lowest in pool model. Data duplication and storage usage. It's the highest in silo and bridge with the database per tenant in PostgreSQL. For example, the system catalog tables, application common tables, and reference tables, right? So, and they are minimal in pool model and bridge with schema per tenant model, but it takes a little bit high when it comes to bridge with the database or silo models. With respect to monitoring, especially the tenant-centric monitoring requires least effort for silo and moderate effort in bridge model and significant effort in pool because all the tenants share all the resources, including tables. And if you need to identify the sequence relates to a particular tenant, it will be very, very difficult. And centralized monitoring, with respect to that, it requires significant effort in silo as you have completely decentralized and isolated at physical infrastructure layer. So you need to have a mechanism to consolidate that data, right? And let's look into hard service limits. Depending on what service you are using in the tenancy stack, it could quickly become a limiting factor for your silo models. And another important factor I would like to highlight is transaction ID wraparound in PostgreSQL. I mean, it is minimal in silo and moderate in bridge and very high in pool models. Since all the tenants share the same table, a single table can quickly reach to the transaction ID. So always have a monitoring and keep an eye and tune your auto vacuum to perform a little. So if needed, it can do a little aggressive vacuuming for you. Right? So You're going to use this decision matrix, and to identify what isolation model works for your multi-tenancy architecture, and whether it is silo, if you have a strict um, uh, regulatory requirements, or you need to have carry tenant specific key for encrypting data at risk, for example. So based on your requirements and based on these decision matrix, so quickly it can help you to identify the model that can work for you. So let's now look into sizing considerations. So in multi-tenancy systems, not all tenants have same capacity or sizing requirements. Some tenants could be more demanding with higher capacity requirements in terms of connections, CPU, memory, networking, IOPS, etc. And other tenants may have different capacity requirements, as you can see in this slide. So the common questions arise are, how do you accommodate different size tenants? I mean, how many tenants you would typically bin pack in a given system? Especially how to identify and isolate noisy tenants proactively in bridge and pool models. And how do you prevent the over provisioning? And how do you optimize, based on actual consumption? And how do you support tiering and SLAs? So there are some common questions you would ask, and so with that, I'm going to take to the next slide, and let's look into each and every dimension, and let's talk about how the tenant bin packing works. So let's look into tenant bin packing, basically to find how many tenants can be accommodated in a database cluster. So there are few critical dimensions you would need to check. So the instance class you're provisioning, of course, comes with a number of vCPUs, memory, networking, etc., and the storage type and IOPS. So it typically applies to RDS, PostgreSQL, and MySQL engines, but for Aurora, there's no limiting on the IOPS. In addition, the total number of connections, the total number of objects, such as the number of databases, schemas, tables, etc., they all come into play when you are talking about the number of tenants you'd like to bin pack into your instance. For example, for Aurora, you get finite amount of local storage, based on the instance class you pick. So which is used by database engine for operations such as sorts, temporary tables, etc. And as for tenants onboarding, you will need to look into the tenant's estimated CPU utilization, IO usage, network throughput, number of connections, number of tables and their size, and estimated growth rate, and of course the temporary space usage for sort operations, or for hash joins, for example, right? And most importantly, the tenant's per process memory usage. And they all drive, right? And when you're calculating how many tenants you want to pack into a single system. So you can use these dimensions for picking up a right instance class in silo. And also, per tenant metrics can help you determine how many you can pack into a given instance class. Finally, the tenant resource utilization change over time, right? It's very important that you have a mechanism to monitor and scale up the compute as needed, and also to move out noisy neighbors to reduce the impact to the co-tenants in the system. So the constant monitoring and capacity adjustments, and imagine that doing across thousands and millions of tenants, it's going to be a daunting task. Especially, you need a sophisticated tooling. So this is where Aurora Serverless V2 can help you out. Whether you are an enterprise with a large fleet of applications backed by several databases, or SaaS and looking for automated capacity adjustments based on the tenant, Aurora Serverless V2 can do this heavy lifting for you. Aurora Serverless is an on-demand auto-scaling configuration for Aurora databases. And in this configuration, your database capacity, the compute capacity is automatically adjusted to meet the demands of your application requirements. And of course, you only pay for the resources you use at that point in time instead of paying for the peak provisioned capacity. So in Aurora Serverless V2, the capacity is adjusted instantly and in fine-grained increments to support even most demanding applications. And that allows you to operate a variety of database workloads worry-free, including multi-tenancy workloads. So we achieve this instant scaling through what we call it as in-place scaling. So the in-place scaling is a non-disruptive operation. So there's a workload going on, and if there's a bunch of in-flight transactions, we don't have to wait for these transactions to complete or pass or find a scaling point. Right? We add these resources on the fly, give it more CPU, more memory, more networking resources, and we let your workload grow. So it scales your database compute without dropping connections, and most importantly, without disrupting in-flight transactions. And we scale also when the workload subsides, we scale down the system. And when we scale down very carefully. So we don't want to flush out the large number of your most frequently used blocks from buffer pool, and which would result in your applications requiring additional I/O to read the same blocks into the memory which we just flushed them out, right? We use a combination of least frequently used and least recently used algorithm to identify and evict cold pages during the scale down operation. So we use Aurora Capacity Unit or ACU to measure Aurora Serverless database capacity. So one Aurora Capacity Unit comes with 2 gig memory with associated CPU and networking. So the starting capacity with serverless can be very low. So you can start with as low as 0.5 ACU, which translates to about 1 gig, and it can scale in as little as in 0.5 ACU in increments. So underneath, it uses scaling factors such as CPU, memory, networking, and automatically adjusts the capacity up and down in fine-grained increments whenever the threshold is reached. So quick recap before we move on to talk about design recommendations for multi-tenancy applications. With Aurora Serverless V2, your database capacity is adjusted on demand automatically and in fine-grained increments without disrupting the workload for your multi-tenancy applications. Basically, you don't have to worry about deploying sophisticated tools to monitor your database compute capacity for your multi-tenancy workloads and taking actions to scale up and down. So Serverless V2 will take care of that for you. So let's now look into the design recommendations. So let's start with design recommendations for performance point of view. Always use database connection proxy, right? The connections are expensive. I mean, every time you connect, disconnect, it causes a frequent CPU context switching if CPU connection ratio is very, very high, right? So use a managed Amazon RDS proxy, which can pull and multiplex your connections in the database and also can help reducing the failover time. So Amazon RDS proxy will retain the connections at the time of the failover and will reestablish the connections immediately after the failover. So the whole operation is transparent to your application, right? So you don't have to worry about implementing reconnect logic in your application code. And you can, of course, you also have a choice to use open source tools such as PG Bouncer for PostgreSQL and Proxy SQL for MySQL. But have a mechanism that continuously monitor and validate your database clusters against the tenants on board. So initially, you're using the decision matrix to find out the number of tenants you want to bin back into the cluster. But over the time, the tenants may start using additional resources. So this mechanism is going to help you out. And with automated scripts, you can have the scaling operations taking place. And of course, as I mentioned in the previous slides, Aurora Serverless V2 can help you this heavy lifting. And for PostgreSQL workloads, try avoiding excessive use of sub-transactions. Sometimes ORM tools, they enable these sub-transactions by default, and excessive use of these sub-transactions can cause a rapid transaction growth, creating contention on lightweight lock during the concurrent sessions when they run heavily, right? And it also makes the vacuum process to work harder and essentially regressing your application performance for all your tenants in the database cluster. Avoid long-running transactions in PostgreSQL. So it will cause bloating and that affects your multi-tenancy workloads. Consider using database parameters such as idle in transaction session timeout, statement timeout in PostgreSQL. Also, as a best practice, set up appropriate TCP creep alive settings and dead connection detection to handle runaway processes consuming database resources. So you can set up parameters such as TCP keep alive idle, TCP keep alive interval, TCP keep alive count, TCP user timeout, and client connection check interval in PostgreSQL. And if you have write-heavy workloads, consider optimizing your system accordingly, such as identifying unused indexes and removing them, taking advantage of hot updates in PostgreSQL, setting up appropriate fill factors in PostgreSQL. Also, partitioning the tables that would help. You can partition your tables by range, hash, or list partitioning, and also you can do sub-partition the segments as needed. Consider keeping partition count minimal in PostgreSQL for better performance. You can use pgpartman extension in PostgreSQL for automatic interval partitioning. If you have read-heavy workloads, you can take advantage of Aurora read replica, and of course, the auto-scaling to scale out your reads horizontally. Aurora Serverless V2 does not support auto-scaling Aurora read replica horizontally, but you can create read replicas, serverless read replicas as needed, which can vertically scale up and down based on your read workload. And you can also look at Aurora Global Database for cross-region read replicas to scale out your reads cross-region while providing cross-region disaster recovery. For RDS, you can either use multi-AZ with 2 readable standbys to scale out your reads, or you can use up to 5 read replicas within region or across region for scaling out your reads on RDS multi-AZ DB instances. And as I mentioned, RDS PostgreSQL version 14 has, you can add up to 155 read replicas with the cascading read replicas to scale out your reads. Now have a mechanism that continuously monitor your system and identify noisy tenants, which is very important in multi-tenancy architectures. And also a process that can help you relocate noisy tenants to isolate them. So you can use AWS Database Migration Service or DMS or logical replication to relocate the noisy tenants with minimal downtime. So now let's look into design recommendations with respect to availability and disaster recovery. Always configure systems with high availability for your critical production workloads. You can use RDS multi-AZ or Amazon Aurora with at least 1 reader. If your writer node is affected and unavailable, we automatically detect and failover. The instance failover typically takes less than 30 seconds on Amazon Aurora. In addition, use AWS JDBC driver for your Java applications to reduce the downtime during the failover. And RDS proxy also will help you to handle database failovers transparently. As I mentioned before, RDS proxy will retain the connections during the failover and reestablish the connections immediately after the failover. And the failovers are really fast when you use RDS proxy. Don't have to worry about the TTL time. And more importantly, always test your failovers periodically to ensure that your entire application stack works as expected and handles database failovers appropriately. Configure backups based on your SLAs and test the backups periodically. You can also leverage database native backup tools such as pgdump, pgrestore in Postgres, or MySQL dump in MySQL to take tenancy level backups in bridge models or pool models. Also, ensure that you have proper DR plan in place for your entire stack. So from control pane to the application pane in your multi-tenancy stack. Amazon Aurora Global Database is designed for globally distributed applications, allowing a single Amazon Aurora database to span into multiple AWS regions. It replicates your data with no impact on the database performance and enables fast local reads with low latency in each region and provides disaster recovery from region-wide outages. Part of your multi-tenancy stack, ensure that you have proper monitoring tenants in place, which can continuously monitor, take automated actions, and generate alarms or notifications based on the thresholds. Major version upgrades require database downtime, and especially when you're using multi-tenancy models with the bridge model, so the impact would be a little bit high. It's going to affect pretty much all the tenants, right? Or even in bridge or pool. So this can impact multiple tenants, hosted on the database cluster. So you can leverage tools such as AWS DMS or logical replication to minimize the downtime during major version upgrades. Now let's look into design recommendations from the point of security. So you can leverage security groups to secure and isolate the tenants to begin with. And you can store application tenant credentials for the databases in Secrets Manager and follow least privilege model so that only that specific tenant can access its credentials. And as best practice, configure your AWS Secrets Manager to rotate tenant secrets for RDS and Aurora periodically. Enable audit logging and set alarms for anti-patterns. You can use database activity stream in Aurora, or you can use PG audit extension in RDS and Aurora for PostgreSQL. And for MySQL, you can use server audit logging, server audit events. The best way to implement authentication and authorization for multi-tenancy model is through IAM authentication. You can have IAM role and a policy to authenticate a tenant to a particular user in the database and leverage database roles and grants for appropriate authorization. In addition, you can use Kerberos authentication, which is only supported in Postgres for RDS and Aurora for now. So it's an external authentication of database users using Kerberos and Microsoft Active Directory. Always encrypt your data at rest and in transit as a best practice. So you can also use extensions such as pgcrypto in PostgreSQL to encrypt critical column data such as social security number, credit cards, etc. As best practice, consider rotating SSL or TLS certificates before they expire. Always use service link roles for cross-service communication with minimal permissions as needed. Finally, the RLS policies, the row-level security RLS policies restrict which rows in a table are returned by select queries or which rows are affected by insert, update, and delete commands in a shared tables in a single schema. So this applies to PostgreSQL only. So now let's look into the example how you can use this row-level security policy in Aurora or RDS Postgres engine. So let's now look into the row-level security and how you can implement it in RDS and Amazon Aurora PostgreSQL. So let's start with initializing RLS. So naturally, you would enable the row-level security at the table level, and you create a policy and you attach the predicate, right? In this case, we are attaching where tenant ID equals to the current user, right? So, and then when the user logs in and when the user queries select start from tenant, what happens is the policy underneath Postgres is automatically going to attach and add that predicate to your query which you are running for the tenant. And what happens is when you run that, it's going to filter out the data and going to return only the data relates to that particular tenant. Right? So especially when you are planning to use pool model, this is going to be a great help for you. So this will enable the security for the table for the tenant so that the tenant can only see his data, not somebody else's data, right? So now let's look into the key takeaways. Hopefully, it's very clear that isolation is the foundation for multi-tenancy design. Ensure that the tenant never cross the boundary to access another tenant data. Authentication and authorization is not an isolation. So always have the proper isolation built in, right? And when you're going with silo model, account limits, always factor in the account limits when you are going with isolation or silo isolation strategy. And use decision matrix for your isolation strategy for RDS and Aurora. We talked about the capacity management, the performance, the backups and recovery, the security requirements, etc. So look into all. See, for example, if your tenant is using large amount of soft space, so the per process memory is going to increase, and multiply that by the number of connections your tenant needs. And when you are bin packing, take that dimension into account. So how many tenants you can bin pack, right? So use the decision matrix. And similarly, use sizing considerations for tenant bin packing. So if I'm going with this many number of tenants, what size of instance I should be using? How you should be monitoring your multi-tenancy workloads, and scale up and down as needed based on tenancy utilization. And always validate that your isolation model is working. So and build a test strategy, and always run these tests to validate your isolation model from the security point of view, from isolation point of view. And as I mentioned, isolation is the fundamental to success in a multi-tenancy environment. So thank you very much for attending the session. And I'll now open up the floor for Q&A. Thank you.